Hello again and welcome to Digital Replay. Still working on Unit 3, Momentum and Energy, but now we're talking about conservation of momentum, which is on pages 376 to 377 of your textbook. So before we talked about what momentum is, and we learned that momentum is the mass times the velocity, or the quantity of speed or motion an object has. But now it's time to lay down the law. So the law states, this is the law of the conservation of momentum. The law states that if no net force acts on a system, then the total momentum of the system does not change. In a closed system, the loss of momentum of one object equals the gain in momentum of another object. In other words, momentum is conserved. So let's dive into this for a minute because this is a lot of words. Let's figure out what this means. So we have Leon and Severin, and Leon's got 20 bucks crumpled up into his pocket in a $20 bill, and Severin has two $10 bills crumpled up into his pockets of his skinny jeans, okay? So what is the total amount of money in the system of Leon and Severin? Well, the total amount of money is the amount that Leon has, or $20, plus the amount that Severin has, which is $20, for a total of $40. So the total system is $40. Now let's say Severin realizes that Leon could use the $10 more than him, so he gives him 10 bucks. So Severin gives Leon 10 bucks. Now, have we changed the total amount of money in the system? Well, let's find out. So let's figure out what Leon now has $30. We add that to Severin's now $10, and we end up with $40 in the system, which is what we had at the beginning. So before these two pieces of the system interacted, we had $40. Then the two pieces of the system interacted, we still have $40. This is conservation of money in this system, but it's the same process, the same principles when we're conserving momentum in a system. So let's take the example of the two carts on the track. Okay, so the two carts on the track lab was a lab where we had two carts on the track and we triggered an explosion between the two carts and we measured the momentum before and after. So what's the momentum before? Well, we take the mass of the two carts, we add that together and we multiply it by the velocity of the system. Well, is there any velocity of the system? So we do mass times velocity. The masses are 0.5 kilograms. So we add those two together and we multiply that by the velocity of the carts. Are the carts have any velocity? No, they're not moving. They're just sitting there. So the total momentum at the beginning was 0 kilogram meters per second. That's the total momentum between these two carts in the beginning. Then we triggered an explosion between the two carts, and the two carts moved away. We calculated their velocity. Well, we measured their velocity using the lab quests. Okay, and what we found was that for cart A, it was a mass of 0.5 kilograms. It moved a velocity of maybe -2 meters per second. We ended up with a momentum of -1 kilogram meters per second because it's moving in the negative direction. For cart B, 0.5 kilos again for this mass. It's moving in the positive direction, so it has a velocity of +2 meters per second and therefore a momentum of 1 kilogram meters per second. Now, if you add the momentum of each of the parts of this system, you'll notice that -1 plus 1 equals 0. 0 was our initial momentum, was the momentum at the beginning of our system. And it still holds true. We still have 0 momentum even after the two carts have interacted and we've had an explosion. Now that's all fine and dandy when the two carts are the same mass. But we needed to do something else to prove this to ourselves that it was the same every time. And so what we did was we added mass to one of the carts. And we ended up with a 1 kilogram cart on one side and a 0.5 kilogram cart on the other side. So again, the total momentum of the system is where we add the masses together and multiply that by the velocity. So 1 plus 0.5 times 0. So again, the total momentum of the system before the explosion is 0 kilogram meters per second. Then we have ourselves a little kapow, a little explosion, right? And the carts move away. And we can even notice that they're moving away at different speeds or different velocities. So now let's do our calculation where we have A, the cart A, having a 1 kilogram mass and moving at a velocity that is measured of negative 1.5 meters per second. We end up with a momentum of negative 1.5 kilogram meters per second. Then for cart B, we have the mass of 0.5 kilograms times the velocity of 3 meters per second, and we end up with positive 1.5 kilogram meters per second. Again, the only reason is because this cart was moving in the negative direction and this cart was moving in the positive direction. So we had velocities here with a negative and a positive direction. So if we add negative 1.5, which is the momentum of cart A, plus the momentum of cart B, which is positive 1.5, if we add those two, we get 0, which is the same as our initial momentum. So our initial momentum was 0 and our final momentum is 0. Momentum is conserved. Now these are explosions, which is two things moving away from each other. But how about collisions, where two things come together and collide and smush? Is it the same? Well, let's find out. Here we have a baseball player sliding into home and collides with the catcher. And it was a pretty major collision, right? So the total momentum is found by finding the momentum of each of the two players. So the momentum of player 1 is his mass times his velocity. So he's moving at about 8.5 meters per second. His mass is 91 kilograms. So his momentum is 773.5 kilogram meters per second. Now the catcher is not moving at the beginning. He's just sitting there, right? So the initial momentum for him is 0 because he's not moving. He has no velocity, therefore he's got no momentum. He's not going anywhere. Okay, so we've got this collision between a moving object and a stationary object. Our total momentum for the system is 773.5 kilogram meters per second because we add the momentum of each of the pieces. We add the momentum of the guy in the red hat and the momentum of the guy in the blue hat. Okay. All right, so that's our total momentum at the beginning. Let's see if after the collision, our momentum is the same, because that's what the law of conservation of momentum says should happen. So after the collision, our 91 kilogram guy in the red hat is moving 4.5 meters per second. You can see he's slowed way down, right? You can see this in the slow motion action replay. You can see this in real life. After he's like hauling it, he just boom, collides and slows way down. Now, the other guy, the catcher, his 93 kilogram mass actually moves. It speeds up. It goes from 0 to 3.9 meters per second. It's hauling now. Okay, so we calculate this out, and we find that this 91 times 4.5 plus the 93 times 3.9 actually equals 773.5 kilogram meters per second. It's the same. It is the same momentum before the collision and after collision. This is the conservation of momentum. This is the conservation of momentum. Now, the types of collisions does matter. Inelastic versus elastic collisions. Do the things bounce? Do they stick together? We'll see that in lab, in class. I'm not going to go into that in too much detail here. Just knowing that momentum is conserved, you calculate the total momentum by finding the momentum of each of the parts. In a perfect system, momentum is conserved when two parts of the system interact. So the momentum does not change. In a perfect system, the momentum will stay the same before and after a collision, before and after an explosion. Now, does it have to be two parts? No, but here in this class, that's what we're talking about, are just two parts of the system. That means that the total momentum at the beginning equals the total momentum at the end. And this is the law of the conservation of momentum. Momentum is conserved before and after an explosion. Usually before an explosion, the momentum is 0 because the items are not moving. And so that means that after an explosion, the momentum will also be 0. Momentum is conserved before and after collisions. Often a collision is going to have a non-zero start momentum, therefore a non-zero start or end momentum because one or both of the objects is moving. The total momentum is the sum of all the momentums in the system. It's the sum of every single momentum, the sum of the parts, right? Just like when we were talking about systems back in Unit 1. All right, that's been your digital replay. If you have questions, come to me in class, comment below, or send me an email, and we'll see you next time.